Okay, and so each of these layers, as I said earlier, has multiple filters, right? Many filters, and each of the filters is producing an activation map. And so when you look at multiple of these layers stacked together in a ComNet, what ends up happening is you end up learning this hierarchy of filters, where the filters at the earlier layers usually represent low-level features that you're looking for. So things kind of like edges, right? And then at the mid-level, you're going to get more complex kinds of features. So, maybe it's looking more for things like corners and blobs and so on. And then at higher level features, you're going to get things that are starting to more resemble concepts and blobs. And we'll go into more detail later in the class on how you can actually visualize all these features and try and interpret what your what kinds of features your network is learning. But the important thing for now is just to understand that what these features end up being when you have a whole stack of these is these types of simple to more complex features. Okay, so the question is, what's the intuition for increasing the depth each time? So here I had 3 filters in the original layer and then 6 filters in the next layer, right? And so this is mostly a design choice. People in practice have found certain types of these configurations to work better. And so later on, we'll go into case studies of different kinds of convolutional neural network architectures and design choices for these and why certain ones work better than others. But yeah, basically the choice of, you're going to have many design choices in a convolutional neural network, the size of your filter, the stride, how many filters you have, and so we'll talk about this all more later. Yeah, so the question is, as we're sliding this filter over the image spatially, it looks like we're sampling the edges and corners less than the other locations. Yeah, that's a really good point, and we'll talk, I think, in a few slides about how we try and compensate for that. Okay, so so each of these layers, convolutional layers that we have stacked together, we saw how we're starting with more simpler features and then aggregating these into more complex features later on. And so in practice, this is compatible with what Hubel and Wiesel noticed in their experiments, right? That we had these simple cells at the earlier stages of processing, followed by more complex cells later on. And so even though we didn't explicitly force our ComNet to learn these kinds of features, in practice, when you give it this type of hierarchical structure and train it using backpropagation, these are the kinds of filters that end up being learned. Okay, so the question is, what are we seeing in these visualizations? And so, right, so in these visualizations, like if we look at this conv1, the first convolutional layer, each of these grid, each part of this grid is a 1 neuron. And so what we've visualized here is the what the input looks like that maximizes the activation of that particular neuron. So what sort of image you would get that would give you the largest value, make that neuron fire and have the largest value. And so the way we do this is basically by doing kind of backpropagation from a particular neuron activation and seeing what in the input will give you the highest values of this neuron. And this is something that we'll talk about in much more depth in a later lecture about how we create all of these visualizations. But basically, each element of these grids is showing what in the input would look like that basically maximizes the activation of the neuron. So in a sense, what is the neuron looking for? Okay, so here is an example of some of the activation maps produced by each filter, right? So we can visualize up here on the top, we have this whole row of example 5x5 filters. And so this is basically a real case from a trained ComNet where each of these is what a 5x5 filter looks like. And then as we convolve this over an image, so in this case, this I think it's like a corner of a car, the car light, what the activation looks like, right? And so here, for example, if we look at this first one, this red filter, like with a red box around it, we'll see that it's looking for, the template looks like an edge, right, an oriented edge. And so if you slide it over the image, it'll have a high value, a more white value, where there are edges in this type of orientation. And so each of these activation maps is kind of the output of sliding one of these filters over and where these filters are causing, where this sort of template is more present in the image. And so the reason we call these convolutional is because this is related to the convolution of two signals. And so someone pointed out earlier that this is basically this convolution equation over here for people who have seen convolutions before in signal processing. And in practice, it's actually more like a correlation where we're convolving with the flipped version of the filter. But this is kind of a subtlety. It's not really important for the purpose of this class. But basically, if you're writing out what you're doing, it has an expression that looks something like this, which is the standard definition of a convolution. But this is basically just taking a filter, sliding it spatially over the image, and computing the dot product at every location. Okay, so as I mentioned earlier, like what our total convolutional neural network is going to look like is we're going to have an input image, and then we're going to pass it through these sequence of layers, right? Where we're going to have a convolutional layer first. We usually have our nonlinear layer after that. So ReLU is something that's very commonly used that we're going to talk about more later. And then we have these conv-ReLU layers. And then once in a while, we'll use a pooling layer that we'll talk about later as well that basically downsamples the size of our activation maps. And then finally, at the end of this, we'll have take our last convolutional layer output, and then we're going to use a fully connected layer that we've seen before, connect it to all of these convolutional outputs, and use that to get a final score function, basically like what we've already been working with. Okay, so now let's work out some examples of how the spatial dimensions work out. So let's take our 32 by 32 by 3 image as before, right? And we have our 5 by 5 by 3 filter that we're going to slide over this image. And we're going to see how we're going to use that to produce exactly this 28 by 28 activation map. So let's assume that we actually have a 7 by 7 input, just to be simpler. And let's assume we have a 3 by 3 filter. So what we're going to do is we're going to take this filter, plop it down in our upper left-hand corner, right? And we're going to do the dot product, multiply all these values together to get our first value. And this is going to go into the upper left-hand value of our activation map, right? And then what we're going to do next is we're just going to take this filter, slide it one position to the right, and then we're going to get another value out from here. And so we can continue with this to have another value, another. And in the end, what we're going to get is a 5 by 5 output, right? Because what fit was basically sliding this filter a total of at 5 spatial locations horizontally and 5 spatial locations vertically. Okay, so as I said before, there's different kinds of design choices that we can make, right? So previously, I slid it at every single spatial location, and the interval at which I slide, I'm going to call the stride. And so previously, we used a stride of 1. And so now let's see what happens if we have a stride of 2. Right, so now we're going to take our first location, the same as before, and then we're going to skip, this time, 2 pixels over, and we're going to get our next value centered at this location. Right, and so now if we use a stride of 2, we have in total three of these that can fit, and so we're going to get a 3 by 3 output. Okay, and so what happens when we have a stride of 3? What's the output size of this? And so in this case, right, we have 3. We slide it over by 3 again. And the problem is that here, it actually doesn't fit, right? So we slide it over by 3, and now it doesn't fit nicely within the image. And so in practice, we just, it just doesn't work. We don't do convolutions like this because it's going to lead to asymmetric outputs happening. Right, and so just kind of looking at the way that we computed what the output size is going to be, this actually can work into a nice formula where we take our dimension of our input n, we have our filter size f, we have our stride at which we're sliding along, and our final output size, the spatial dimension of each output size is going to be n minus f divided by the stride plus 1, right? And you can kind of see this as as a, if I'm going to take my filter, let's say I fill it in at the very last possible position that it can be in, and then take all the pixels before that, how many instances of moving by this stride can I fit in, right? And so that's how this equation kind of works out. And so as we saw before, right, if we have n equals 7 and f equals 3, if we want a stride of 1, we plug it into this formula. We get 5 by 5 as we had before, and the same thing for 2. And with a stride of 3, this doesn't really work out. And so in practice, it's actually common to zero pad the borders in order to make the size work out to what we want it to. And so this is kind of related to a question earlier, which is what do we do right at the corners? And so what in practice happens is we're going to actually pad our input image with zeros. And so now you're going to be able to place a filter centered at the upper right-hand pixel location of your actual input image. Okay, so here's a question. So who can tell me if I have my same input 7 by 7, 3 by 3 filter, slide 1, but now I pad with a 1 pixel border, what's the size of my output going to be? So I heard some 6s, heard some 7s. So remember we have this formula that we have before. So if we plug in n is equal to 7, f is equal to 3, right? And then our stride is equal to 1. So what we actually get, so actually this is giving us 7 by 4. So 7 minus 3 is 4, divided by 1, plus 1 is 5. And so this is what we had before. So we actually need to adjust this formula a little bit, right? So this was actually, this formula is the case where we don't have zero padded pixels. But if we do pad it, then if you now take your new output and you slide it along, you'll see that actually 7 of the filters fit. So you get a 7 by 7 output, and plugging in our original formula, right? So our n now is not 7, it's 9. So if we go back here, we have n equals 9 minus a filter size of 3, which gives 6, right? Divided by our stride, which is 1, and so it's still 6, and then plus 1, we get 7, right? And so once you've padded it, you want to incorporate this padding into your formula. Yes, question. So in like 7. Okay, so the question is what's the actual output of the size? Is it 7 by 7 or 7 by 7 by 3? The output is going to be 7 by 7 by the number of filters that you have. So remember, each filter is going to do a dot product through the entire depth of your input volume, but then that's going to produce one number, right? So each filter is, let's see if we can, go back here. Each filter is producing a 1 by 7 by 7 in this case activation map output, and so the depth is going to be the number of filters that we have. Sorry, let me just 1 second go back. Okay, can you repeat your question again? Okay, so the question is, how does this connect to before when we had a 32 by 32 by 3 input, right? So our input had depth, and here in this example, I'm showing a 2D example with no depth. And so, yeah, so I'm showing this for simplicity, but in practice, you're going to multiply throughout the entire depth as we had before. So your filter is going to be, in this case, a 3 by 3 spatial filter by whatever input depth that you had. So 3 by 3 by 3 in this case. Yeah, everything else stays the same. Yes, question? Does the zero padding add some sort of extraneous features at the edge of the image? Yeah, so the question is, does the zero padding add some sort of extraneous features at the corners? And yeah, so I mean, we're doing our best to still, get some value and do process that region of the image. And so zero padding is kind of one way to do this, where, I guess we can we are detecting part of this template in this region. There's also other ways to do this that you can try and like mirror the values here or extend them, and so it doesn't have to be zero padding, but in practice this is one thing that works reasonably. And so yeah, so there is a little bit of kind of artifacts at the edge, and we sort of just you do your best to deal with it. And in practice this works reasonably. I think there was another question. Yeah, question. So if we have non-square images, do we ever use a stride that's different horizontally and vertically? So I mean, there's nothing stopping you from doing that. You could, but in practice, we just usually take the same stride. We usually operate over square regions, and we just, yeah, we usually just take the same stride everywhere. And it's sort of like, in a sense, it's a little bit like the resolution at which you're, looking at this image. And so usually there's kind of, you might want to match sort of your horizontal and vertical resolutions. But yeah, so in practice you could, but really people don't do that. Okay, another question? Why? So the question is, why do we do zero padding? So the way we do zero padding is to maintain the same input size as we had before, right? So we started with 7 by 7, and if we looked at just starting your filter from the upper left-hand corner, filling everything in, right, then we get a smaller size output, but we would like to maintain our full-size output. Okay, so yeah, so we saw how padding can basically help you maintain the size of the output that you want, as well as apply your filter at these like corner regions and edge regions. And so in general, in terms of choosing, your stride, your filter size, your stride size, zero padding, what's common to see is filters of size 3 by 3, 5 by 5, 7 by 7. These are pretty common filter sizes. And so each of these, for 3 by 3, you will want to zero pad with 1 in order to maintain the same spatial size. If you're going to do 5 by 5, you can work out the math, but it's going to come out to, you want to zero pad by 2, and then for 7, you want to zero pad by 3. Okay, and so again, the motivation for doing this type of zero padding and trying to maintain the input size, right? So we kind of alluded to this before, but if you have multiple of these layers stacked together, so if you have multiple of these layers stacked together, you'll see that if we don't do this kind of zero padding or any kind of padding, we're going to really quickly shrink the size of the outputs that we have, right? And so this is not something that we want. Like you can imagine if you have a pretty deep network, then very quickly the size of your activation map is gonna shrink to something very small. And this is bad both because now we're kind of losing out on some of this information, right? Now you're using a much smaller number of values in order to represent your original image. So you don't want that. And then at the same time, also, as we talked about earlier, you're also kind of losing sort of some of this like edge information, corner information that each time we're losing out and shrinking that further. Okay, so let's go through a couple more examples of computing some of these sizes. So let's say that we have an input volume, which is 32 by 32 by 3. And here we have 10 5 by 5 filters. Let's use stride 1 and pad 2. And so who can tell me what's the output volume size of this? So you can think about the formula earlier. Sorry, what was it? 32 by 32 by 10. Yes, that's correct. And so the way we can see this, right, is so we have our input size, F is 32. Then in this case, we want to augment it by the padding that we added onto this. So we padded 2 in each dimension, right? So we're actually going to get total width and total height is going to be 32 plus 4 on each side. And then minus our filter size, 5, divided by 1 plus 1, and we get 32. So our output is going to be 32 by 32 for each filter. And then we have 10 filters total. So we have 10 of these activation maps. And our total output volume is going to be 32 by 32 by 10. Okay, next question. So what's the number of parameters in this layer? So remember, we have 10 5 by 5 filters. 250. Okay, so I heard 250, which is close, but remember that we're also, our input volume, each of these filters goes through by depth. So maybe this wasn't clearly written here because each of the filters is 5 by 5 spatially, but implicitly we also have the depth in here, right? It's going to go through the whole volume. So I heard, yeah, 750 I heard. Almost there. This is kind of a trick question because also remember we usually always have a bias term, right? So in practice, each filter has 5 by 5 by 3 weights plus our one bias term. We have 76 parameters per filter, and then we have 10 of these total, and so there's 760 total parameters.
컨브넷에서는 여러 개의 필터들이 서로 스태킹 되는데 초기 단계에는 로우 레벨 피처를 익스트랙트하고 중기에는 미들 레벨 피처를 후기 단계에는 하이 레벨 피처를 익스트랙트하게 됩니다. 이번 사례는 자동차의 백라이트 이미지를 32개의 5곱하기5 필터로 처리한 것입니다. 빨간색으로 표시된 첫 번째 액티베이션 맵의 경우 엣지가 하이라이트 된 것을 볼 수 있습니다. 반면에 파란색 박스로 표시된 액티베이션 맵의 경우 라이트 부분이 하이라이트 되어 있는 것을 볼 수 있습니다. 다음 단계의 필터들은 이러한 이미지들을 컴바인하여 더 복잡한 피처들을 익스트랙트 하도록 합니다. 다음은 간단한 컨볼루셔널 뉴럴 네트워크의 사례입니다. 레이어들은 컨볼루션 레이어와 non-linear value 레이어 그리고 액티베이션 맵을 다운샘플링하는 풀링 레이어들로 이루어져 있습니다. 마지막 단에는 fully connected 레이어를 통해서 final score 펑션의 값을 얻도록 합니다. 이번 사례의 경우에는 car부터 horse까지 5개의 클래스가 있는데 car가 가장 높은 점수를 받아서 올바른 클래시피케이션이 되었습니다. 이번에는 필터가 어떻게 컨볼브하고 슬라이드 하는지 살펴보도록 하겠습니다. 먼저 좀 더 간단한 문제를 풀어보도록 하겠습니다. 여기서 이미지 사이즈는 7 곱하기 7이고 필터 사이즈는 3 곱하기 3으로 하겠습니다. 처음 시작은 이미지의 upper left 코너에 필터를 위치시키고 녹색 부분으로 표시된 9개의 점들에 대해서 dot product를 구합니다. 다음은 슬라이드 오퍼레이션으로 한 칸 이동한 뒤 마찬가지 방법으로 dot product를 구합니다. 박스가 오른쪽 끝에 다다를 때까지 이러한 오퍼레이션을 계속합니다. 그 후에는 한 칸을 내려서 왼쪽부터 다시 오퍼레이션을 시작합니다. 모든 오퍼레이션이 끝나면 5 곱하기 5의 아웃풋이 만들어집니다. 이번에는 스트라이드의 크기를 1에서 2로 증가시켜 보겠습니다. 이렇게 두 칸씩 이동하면 최종적으로 3x3의 아웃풋이 만들어집니다. 이번에는 필터의 스트라이드를 3으로 증가시켜 보겠습니다. 필터의 크기가 인풋 이미지와 맞지 않아서 제대로 동작하지 않는 것을 볼 수 있습니다. 지금까지 배운 것을 식으로 정리하면 다음과 같습니다. 인풋 이미지 크기를 n 곱하기 n으로 하고 필터 크기를 f 곱하기 f로 했을 때 아웃풋 사이즈는 n 빼기 f 나누기 stride 더하기 1이 됩니다. 다음은 인풋 이미지의 보더에 제로 패드를 더하는 방법을 알아보도록 하겠습니다. 예를 들어 인풋이 7 곱하기 7이고 필터는 3 곱하기 3일 때 스트라이드는 1, 패드는 1이라고 하면 아웃풋은 7 곱하기 7이 돼서 인풋 크기와 같아지게 됩니다. 컨볼 레이어에서 만일 우리가 제로 패딩을 통해서 인풋 사이즈를 유지하고자 한다면 스트라이드가 1일 경우 F가 3이면 하나의 제로 패딩을, F가 5이면 2개, F가 7이면 3개의 제로 패딩을 사용합니다. 지금까지 학습한 내용을 인풋 볼륨이 32 곱하기 32 곱하기 3인 경우에 적용해 보도록 하겠습니다. 10개의 5 곱하기 5 필터가 있고 스트라이드가 1인 경우, 패드가 2인 경우에 아웃풋 볼륨 사이즈를 계산해 보도록 하겠습니다. 계산 결과는 32 곱하기 32 곱하기 10이 됩니다. 다음은 이 레이어를 구현하는 데 필요한 파라미터의 수입니다. 즉, weight와 bias의 숫자들입니다. 각 필터마다 5 곱하기 5 곱하기 3만큼의 weight 값들이 있고 한 개의 bias가 있습니다. 따라서 각 필터마다 76개의 파라미터가 있습니다. 10개의 필터들이 있기 때문에 총 760개가 됩니다. forward propagation을 통해서 로스 값이 계산이 되면 back propagation을 통해서 이 weight와 bias 값들이 변하게 됩니다. 그것이 바로 트레이닝입니다.